Okay. Right. Greeting from Thailand. And good morning, everyone. I thank you, Yi, for the introduction to the project and I think very important points on the timing, on the different part of learning strategy that actually I also utilize them in creating the computational realization of the learning model that we are trying to do here. So the title of the talk that of my part is learning of Thai syllable, which will be about the because actually my work mostly focus on the a learning algorithm, how to create a better learning algorithm, or how to create a different text of the learning algorithm that we can improve the efficiencies of the learning process. And also at the same time, emulating what really happened in human vocal learning there. Okay, so for the key points of the work that I had been doing, I think just this year, in 2012 and 2022, we had the paper out on the usage of deep learning together with different types of learning strategy in order to create an inverse model that could predict or estimate potential articulatory targets from acoustic data. So the key point here is that because in learning, we usually don't have something like a large amount of learning materials. We may only have like a few instances of learning samples, and then from there, the learner can emulate and then can practice and then can learn from those examples and be able to try and to become skills in controlling the articulatory part of the speech production. So in that sense, in order to emulate that, we think that there must have been a certain mechanisms that allow humans to be able to estimate potential location of articulators that they can produce. So those are the idea. And another thing is that from our previous work that we have been trying to use optimization to address this problem, we found that it requires quite a long time in optimization and quite computational resource in order to make it works. Partly it might be because of the optimization algorithm that has been used. Another might be because of that's the idea of comparing the end results and then trying to adjusting the correct articulators at the beginning to fit in those frames might be the difficult problems that we may have a better way to address that. Okay, so the idea would be to how can we create a model that you don't have to train them, but it's like it has been trained for a longer period of time, maybe based on the evolution, based on the articulatory construction that we have, and it should be able to comprehend the trajectory or comprehend the estimated targets based on the perceived features in the acoustic levels. So those are the ideas behind the papers that we published in 2022 here. Okay, so in that sense, we are trying to represent the learning process as a process of recognizing the potential movement and then trying to test them whether they are correct or not. And then if they are not, then use those to improve the correctness of the model. This is actually, if you think about this and then comparing to the previous approaches that we have been doing in learning the articulatory parameters, it's nothing new. right? We have been doing this using optimization, using different approach, but each of those try out, we found that there are actually certain instances in learning process that the algorithm may not be able to explain. Like it only explain the part that we are trying to frame. For example, in our previous takes in 2014, we proposed that in order to learn the functional component, computative functions of the in speech prosody, we can consider them as layers of information that are laying on top of one another. And then we can then think of them as combinations. And once we have like those combinations, these represents the targets. This represents the target of that instance, which can then be optimized using the optimization algorithms. So for example, in this case, once we partition the layers and then obtaining the categories, we can then estimate parameters. There will be like 6 sets of parameters that can be estimated in order to represent these functions that we have here. So from this, instead of estimating parameters of the model utterance by utterance, we are now able to estimate the underlying parameters of those functions, which represent the way that the way to communicate in those style. Then for articulatory optimization, in 2014 as well, we also try to do the same thing. Actually, this is also the one that Yi has already mentioned, that we're trying to optimize the articulatory parameters of vocal tract lab using the analysis by synthesis approach by comparing the actual speech and the predicted speech, and then use this comparison on the acoustic level to adjust the parameters, and then keep doing this multiple times and adjust the parameters so that it would converge. The error would converge to the low value, and then we would have a certain set of parameters that should represent the vowels that we're trying to convey. And by incorporating this with the target approximation framework, so instead of just in the prosody case, we have M, B, and lambda. We have 3 parameters per segments. In this case, you would have like a bunch of articulatory parameters that need to be optimized. And for different vowels, each vowel would have one set of parameters that represent those vowels, and then we can let the rest, the version of the rest, be taken care of by the articulation of the movement of the articulators. So we tried that in 2014. It's okay. It can estimate the underlying parameters, but it takes quite a long time in parameter optimization. And I think later that and he has improved the algorithm further and can accelerate it certainly a bit there. But it still struck my mind back then that there should have been a better way that we could address this problem, because it's true that for this one, we can learn the underlying articulatory targets based on acoustic data. But this is like starting from a blank sheet of paper, right? Starting from the random state. And then we're trying to construct that, right? Construct those parameters from randomness into the predicted one. It's okay. But because if we look at human learner, we can see that for human, when one perceives a certain maybe unfamiliar vocal articulations, they may be able to estimate on or reproduce that sounds. But how could they, right? How could they be able to do that? There must have been some way that allowed them to be able to mimic those sounds out. You'll be able to estimate the trajectories. So my idea back then was to trying to create a model that should be able to inverse the process, that you don't have to repetitively adjust the parameters, but by perceiving the acoustic data, you should be able to guess what types of articulatory configuration that should be. So that's the idea. But how could we achieve that algorithmically? So in order to think about this, we need something like this. In order to like mimic the process of human learning, right? In order to be able to recognize the potential articulatory movements once you receive the data, we have a types of a mapping model, right? The inverse model that should be able to convert from acoustic data and then estimate certain locations based on the acoustic data, the location of the articulation of the target. But in order to do so, right, we would need for this one, it's very obvious for me, right, that okay, for the mapping task, we need to use a types of deep learning approach. However, for that to work, we need to have a really large size data set. We need to have a very large data with lots of variations to train the model to be able to comprehend the variation, and also pairing with articulators. Right? We don't have that. Okay, so we need to have a way to generate those data, to explore the vowel space, to create a types of learning that may have been done, but that may have been there in the that allow us to be able to guess or to mimic those pronunciation. So in order to do that, we need a way to create the data for the model. And that should allow us to explore the multiple configurations, and should be able to allow us to explore like the progression of speakers, as well as like different head configurations of the speaker as well. And lastly, in order to improve the model correctness in prediction, right, we need some types of learning model, which combining the inverse model and model learning is quite obvious that we need to have a types of mapping model that allow us to do the job, but it's still stuck on how to have the data for training the model. So we come up with this, that based on the initial configuration that we have from the VTL, there are a number of predefined vowel, predefined German vowels. But I would like to say that those are the predefined phonetic vowels that we have in the for the vocal tract labs, which spread all across the vowel space. For that, and also we it's good that Peter's implemented a program in such a way that you can also configure the anatomy or the head configuration of the vocal tract, and it allows to insert certain influence, insert certain variation into those configuration and generate the data. So in terms of training, right, we create the deep learning model based on the generated data. These data are learned from the predefined German vowel, but there are only like a set of them. Right? There are only a set of them. How could we be able to generate a lot of variations that satisfy the requirement of deep learning in order to remember the variation and the pattern, the co-articulation pattern that occur in acoustic speech? Right? We utilize the strategy of combining exploration and exploitation in optimization by creating the exploration part in data generator, that we creating a types of vowel space, and then sampling from those vowel space the configuration of the potential configuration based on the predefined vowel. Those potential configuration will be the interpolated version of this vowel, and then pre-process them in the disyllabic manner, and use those in order to learn the pattern using deep learning, using the bidirectional LSTM. And then afterward, we use this to train the model, right? Because once we have the data generated from the data generator, we will also have acoustic data together with that, because we can use the VTL to generate the acoustic part as well as the articulatory part. Then we create a mapping model based on deep learning. And for prediction, for estimation, once we have the targeted speech, we can perform estimation and then use them in articulatory synthesizer in order to create the imitated. Actually, use the deep learning, and then we will have the articulatory representation, the articulatory targets, which can then be used with the VTL to produce the imitated speech. So it means that in our take here, we use only the initial data that we use to train the models are from the predefined vowel specifications. And then we create a types of exploration on those vowel space to train the deep learning model. So that in that sense, we have a types of experimentation that the learner might have, that they produced a certain vowel out and perceive that acoustic variations. And by pairing those together, we are able to train a model that could quite accurately predict not just data from the vowel space, the original vowel space, but also from the recorded data of Thai vowels, and then comparing the resynthesized version of these together with the original, we found that they are quite acceptable to a certain extent. And we also evaluate the model by comparing the recognition accuracy as well and listening tests. So there are quite a lot of things that we have done in order to evaluate this approach. Okay, so you can see that the key idea of this is to implement the data generation model that could allow the mapping model to learn based on experiment. In that regard, we focus on the exploration. Well, when we talk about optimization algorithm, there are always trade-offs between exploration and exploitation. In optimization, exploration means that it means the ability of the algorithm to explore the solution space, and exploitation is the ability to fit the data that you have with the model. So balancing between the two allows us to get the best learning parameters from the data that we have, or from the situation that we have here. So since it is exploitation, we leave that to the deep learning approach to train based on the set of parameters and acoustic data that we generate. Then we then focus our approach, our attempts on creating the exploration model, creating a data generator that could explore the vowel space and produce enough variations for the model to learn. In that, we identified like 3 important parts that need to be done in order to generate those data. Right? The first part is the exploration of the articulatory space, right? Because as you can see that initially we have only like the location of articulators to begin with. And we need to have a way that could explore the possible combination, the entire possible combination, or you could say that in exploring the articulatory configuration space so that it could generate the data to feed the model to learn. For that, we create a very simple articulatory interpolation algorithm using that we use like the data that we use in training would come from the interpolation, right? The sampling from 2 vowels. So we kind of sampling the 2 vowels and then sampling the value of U, and then we get R as representation of the configuration. And then we use this to generate acoustic data. And then we keep doing that multiple times in order to get the data with enough variations in the exploration. But doing that, we would only have the data just from one speakers. And as he said, that speaker normalization is one of the important points that we want to address in optimization. How could we allow the model, because deep learning model is kind of very easy to get stuck in terms of overfitting. In order to avoid that, we need to have like data from multiple speakers, but we don't have those configuration to train. So we also do the sampling as well, because we have like, back then we have like shy vocal tract and then adult vocal tract. So we create a sampling model that sample between the two. So we have like a multiple progression from the child vocal tract to adult vocal tract. Have to admit here that some of the sampling will be, this will still be represented by just interpolation between the two. There might be other variations that have not been covered in the study though. And lastly, we also, because for the deep learning to be able to generalize, we need to have like a lot more variations, especially in terms of acoustic part. Because, for example, the recorded data would be different from the data generated from VTL. So we need to have a way to create a more like robust model. And in order to do so, we conduct a standard data augmentation, like insert random noise, randomly increase the volume of the sounds, and also doing the pitch shifting, the whole thing, and also perform feature masking. And that means we just crop the data, part of the data out. That will be the part of the data after generated. And then using the data generated from this explore space to train the deep learning model with the speech feature as input and articulatory targets as output. Right, the model we use is the RNN, recurrent neural network, the bidirectional LSTM, with the optimizer, and use MSE on the target as the loss function. Okay, I think I should go a little bit quicker here. And then we perform the evaluation, right? Training model, we perform the evaluation on multiple fronts. Right? We evaluate the model of the estimated target. For the estimated target, we use RMSE and R square, right, to estimate it, whether it can predict the targets close to original or not of the synthetic data set. And we also evaluate the acoustic domain of the resynthesized sounds using the MAPE on F1, F2, and F3. And we also perform the perception tests with computer perceptions. This is quite an idea that my student had, that he trained the speech recognition model that used bidirectional LSTM to train speech recognition model based on the recorded data, and then use that to benchmark to see whether the resynthesized versions, resynthesized sound, could be able, whether the recognizer will be able to classify the recognized sounds or not. So that's one of the computer perception. And we also did the listening test to see the identification rate. Right. So initially we try to explore the data to see that from the training data set we use UMAP to see the distribution, and we see that, okay, for the German vowel, the data generated of each German vowel that we sample and the one that close to them are quite close to one another. And when we're looking at the test set MFCC using UMAP, you can also see that there are certain separation in the acoustic sense. So we hope that by training the articulatory data set target here, and in comparison with the acoustic features, we should be able to create an inverse model that should be able to inverse this data back to the articulatory targets and then reproduce it back as well. So for the results of the synthetic data set, these are the data set that we explore the vowel space. Comparing from the baseline, the simple linear regression with the bio-STM for the monosyllabic and disyllabic, you can see that the requirement is quite drastic. That's quite obvious, like when you compare the simple regression with the deep learning. But also you can see that with high R square and RMSE about actually 0.1. This indicate that comparing between the two, This indicates that it can consistently produce the result. But as Yi suggested, that evaluating it this way might not reflect the human perceptions. So we try different way of evaluation as well. So this is the result on the acoustic articulatory targets, right? And these are the results of the MAPE on the predefined vowels. So these are still on the synthetic data set, the German vowels. And then we try to see whether the model can estimate the acoustic data, can estimate the target that produce the acoustic data that have like close characteristics to the original. And from the error is about 7% to 10%, which comparing to the previous optimization work, they are quite comparable, but a lot faster in this case, because after we train the model, prediction is pretty fast because you're kind of converting from acoustic to articulatory data directly based on estimation. Then we test it with the Thai vowel, right, using the Thai recorded speech. I think the easier way is to look at this F1 and F2 chart, which the red dot indicate the target and indicate the originals, right? And the blue dots refers to the estimated configurations. So they are close to one another for some of them, but for some, you can see that they are quite far away in terms of F1 and F2 if we look at it this way. But if we were to match the forming range of the empirical forming range and the estimated range, we could see that the distribution of the F1 and F2 comparing between vowels, for this one, the blue and the red, these are both from the re-synthesized data, but they are from the first syllables, and the red one are from the second syllables. You can see that they kind of locate on the similar range to the empirical formings. In terms of spectrogram, comparing of the original and the inverted one, and you can see that the transition between vowel to vowels and the location of vowel are quite close to one another. Right? This one is for R and E, right? From R and E from of the original and of the inverted version. Yes, these are from like U and E, right? You can see that it have very similar trajectories. So as you can see that evaluating in numerical sense, we tell you that, okay, it fits so to a certain extent, and it can reproduce the results. But whether it would be able to be recognized by human or by recognizer is another matter. So we did the perception test on computer, on the speech recognition, and on the listening test. For the recognition test using the speech recognition model, we also further test the benefit of the speaker simulation and data augmentation, and look at whether it improves whether it improves the model in order to estimate the articulatory targets or not. And as shown in this table, you can see that with all the data generation approach, we got the precision in terms of the recognition rate for the models about 0.82. Without speaker simulation, it dropped a bit, and without data augmentation, it dropped even further, right? And without both, you can see that it even dropped down further. That means having variation and both speaker simulation and data augmentation here allow the model to be able to kind of capture the consistent patterns and then be able to map from the acoustic part to the articulatory part. The confusion matrix show that most of the errors occur from the This is R and O sound, the R and O sound here. That the misclassification mostly occur for the O sound, and we use the same data set. We use the same synthetic data set to test in the listening test, and we also found that listener also have problem with the O sound as well. So for this one, we think that because you can see that for the O sound, a lot of confusion occur with together with an R sound. So the difference between both are only the lip routing. So potentially, in our case here, the data, the way that we generate data here might not represent this case well in terms of lip routing and other cases. All right. So these are the work that have been done for the project. What's next? So from this point on, you can see that we can create the inverse model that estimate the articulatory targets based on the acoustic data. But the problem that we see in terms of creating the learning algorithm here is that we have to predefine the segmentation boundaries and before learning the parameters, which in reality this might not be well. You have now you have like two problems. You have to also learning the segmentation and learning the targets together. So the next step from this would be to find a way to learn the segmentation, right? Or creating an algorithm that is independent of the segmentation and still able to learn the variation in the targets, because target approximation model imposes quite strictly that you need to have like the end of the target in order to transition to the next one, to use the next parameter. So there must be a way to represent this type of mechanisms. And the second one would be to like pursue on the learning of consonant coda. I think, and she might have more to add there later. And the last one is like one of the thing that I'm interested right now is to create something like a self-supervised or reinforcement learning environment that the model could be able to learn that inverse model, not just from the data, but also from improving itself further. Okay. So these are all of the work in my part.